We're making a video about nothing, yeah. There are kind of two types of nothing. One is like nothing with a little n. I would sort of define as the absence of something. So, you've got a sandwich there, Brady. I take it off you, and now you've got nothing. So it's the absence of something. That's one nothing. There's another one which is like nothing with a capital N, if you like an absolute concept. Like a true nothing. This is a nothing which never has the potential to be something and has never been something. It's not something you're going to get from taking something away. It's never been something. It's hard to, as a physicist, to imagine how that could ever have a place in our universe, could ever be real, right? If it does exist, I think it would have to be disconnected from our universe. As a physicist, I think I'm more interested in the first form of nothing, which is nothing with a little n. So what might that be? You might think about the vacuum, empty space. That's nothing, right? Space is empty. But there's always a little quantum wiggle in the fields that can, in principle, live in the vacuum. And the way this manifests itself is you can imagine like little virtual particles popping in and out of existence over a very short time period in this quantum vacuum. And that effect actually gives the vacuum an energy, gives it a vacuum energy, which could be the origin of dark energy.
What are these things that are popping in and out of existence? Why are you calling them virtual?
In some sense, a particle is a fluctuation in a field. That's what a particle is. But these aren't particles that you can have. They're never there at the beginning. They're never there at the end. They're just the sort of mess in the middle. But you can never step in and grab one. They're really just a sort of a word that we use to describe the fluctuation in a field due to quantum effects. The fact that we really live in this quantum environment, not a classical environment.
But it does create an energy and a pressure that acts on the universe.
Absolutely, yes, it would. And so this is the reason that I would say that the vacuum is not nothing, because it's got energy, for example. It carries an energy density, which may or may not be driving the acceleration of the universe. So it's definitely not nothing. So is there even a nothing? So I've talked to you about Ed Witten before. He's a very smart guy, Fields medalist, great physicist. In 1982, which I think was the year Aston Villa won the European Cup, a bit random. So in 1982, he actually discovered a nothing. So he was messing about with some solutions to Einstein's equations describing gravity and space-time. He realized in certain situations you could have what's called a bubble of nothing. So this is wild. This is what you should imagine, right? Is that you've got some space-time, maybe this room, right? And suddenly there's an instability, and a bubble appears. Inside that bubble is literally nothing.
It's not a vacuum.
It's not a vacuum. It is nothing. So you can imagine, right? So imagine this bubble. This bubble will grow, by the way. So you can see your sofa there in your lounge, right? Bubble then engulfs the sofa. It's not like the sofa just disappears. The actual space that the sofa was occupying also disappears. It just ceases to exist. So the reason this happens, the precise nature of Witten's bubble of nothing was he has to have like a compact direction, so that one of his directions goes round in a loop like a circle, and that size of that circle pinches off to nothing, and that's the location of his bubble. So Witten found this bubble of nothing, right? And you're like, okay, this is kind of scary.
He thought of it, he didn't find one.
Well, he thought, yeah, fair enough. There's no experimental verification, but he saw it within Einstein's equations, right? That certain situations you could have an instability towards a bubble of nothing literally appearing. Two physicists, Brown and Darlin, they came up with a really weird take on what nothing might actually be based on what Witten had done. So they claimed that nothing could also be thought of as infinitely negatively curved space-time. So let me explain what that is. So the way we really think about gravity and the way that Einstein taught us is in the curvature of space-time. So that curvature can be positive, like the curvature of a sphere, or it can be negative, for example, a bit like the curvature of a saddle. Okay, so there's two different types of curvature, positive and negative. When it comes to space-time, when we talk about negative curvature, we talk about something called anti-de Sitter space. And so what Brown and Darlin were claiming was, as you take the curvature of this anti-de Sitter space to minus infinity, it becomes nothing. The way they realized this was, they basically said, right, we're going to take a space-time, we're going to put a bubble in it, But in that bubble, we're going to put another space-time which is going to have some negatively curved space. Okay, and then we're going to drive that curvature down towards minus infinity. And as they did that, they realized that they were starting to recover Witten's bubble of nothing. So they sort of speculate, okay, so maybe this is how you should think of nothing as actually infinitely negative curvature. And actually, there's another reason to believe it now that we understand, is that when you've got these negative curvatures, they admit what's called like a holographic description. So there's two ways to describe negatively curved space. You've got just your gravity of negative curvature, and there's this other description. So it's called the ADS-CFT's correspondence. So the ADS part tells us about the negative curvature, and then we have this thing called the CFT. And these are just two different languages describing exactly the same physics. So think of one as being like English and the other one like Japanese, but they're both describing the same physics. They're just different ways of doing it, right? So you've got your ADS side, which is like describing your negatively curved space, and there's this other CFT side, which is just a different language. And here's the weird thing. So it's a language, so it kind of has a number of words, or more precisely, numbers of degrees of freedom. But think of it as a number of words in that language. So the number of words on the CFT side, that correlates with the curvature of the ADS side. And as you put that curvature towards minus infinity, the number of words on the CFT side goes down to 0. So it literally ends up like a language with no words. It's describing nothing, right? So this is starting to believe that this is actually what nothing really is. It's really infinitely negatively curved space.
But does it have a volume? If there was a bubble of one of these bubbles of nothing in the room, could I measure its like diameter?
It's a very good question. Yes, you could measure the diameter in your space, but actually it's true. In the infinitely negatively curved space, distances go to 0. Actually, they do. They go to 0 size. That's another feature of it.
What would happen if you jumped into the bubble?
There's nothing to jump into. There's nothing there.
Would you see anything?
You can't go into it. There's nothing there. There's nothing literally to jump into.
But if the bubble of nothing was between you and I,
it's nothing. You shouldn't think you can go into it. What are you going to go into? There's nothing there. Like a nothing. It's not even space. There's no space-time there. It's infinitely negatively curved. If you want to think of it in that way, all distances are suddenly getting shrunk to zero. It's gone. But if it gets weirder, right? Okay, so there's something called the...
Isn't this a bit like, you know how sometimes when you're trying to figure something out, like in the real world,
yeah,
and you can use a polynomial or something to do it, and you get two roots, and you get a positive root and a negative root, and you throw the negative root away because it has no meaning in the real world. Is this just like Einstein's equations have a few results that are meaningless, like are silly and meaningless, and we should just ignore them?
Quite the opposite. Okay, this is where I'm going to tell you the next bit of information. So more recently, two physicists called Jake McNamara and Qumran Vafa, they were both at Harvard at the time, they came up with something called the cobordism conjecture, which is a fancy word. Don't worry about what that is. But what they were saying was that all different string theories are kind of connected. They're dynamically connected in some way. So all different quantum gravity theories, if you like. So let's say you have your favorite theory of quantum gravity, Brady, which I'm sure that you have, right?
Vanilla.
yeah. And I've got my favorite theory of quantum gravity, right? What they're claiming is that there's always a way to dynamically transition from my theory to your theory. So if I live in a world where it's described by my theory, there is a way to dynamically transition to a world with your theory. Okay, this is what their conjecture says. And they've got good reasons to think that this might be true. But now we bring Ed Copeland along. Now, Ed Copeland, he has his favorite theory of quantum gravity. But he's a simple man, our Ed, isn't he? He's a man of simple tastes. And his favourite theory is the trivial theory of quantum gravity, the theory of nothing at all. It's not a very exciting theory, but it's still a theory, right? The trivial one. But we've just said that there's always a way to dynamically transition between any theory of quantum gravity. So you start out in your world with your theory of quantum gravity and all the stuff that's going on. And then there is a way to dynamically transition from your situation into Ed's. It can always happen. So that means there's a way to dynamically transition from you to nothing. Okay, so this is really quite remarkable. That passages are always there and always available to you. In principle, it might take a lot of steps, it might be complex, but nevertheless it should be there. You see it in Witten's bubble of nothing, but that's just one example. And actually they go further. It suggests that actually within within quantum gravity, there should be always these dynamical objects that allow this transition to happen. And they go by the name of end-of-the-world brains. So an end-of-the-world brain is literally that. Beyond it, there is nothing. There is nothing beyond it, because it's the thing that gives you the transition from our world, or our world, to nothing. It's an end of the world. And this all comes from these ideas about linking quantum theories of gravity to one another. So one of the things that we were playing around with, that we started thinking about, is...
Who's we?
Me, Ben, my student Ben, and Paul Saffin here at Nottingham. So we started thinking about, could you live on an end-of-the-world brain? Could we literally be living on the end of space, right on the edge of nothing? And actually, remarkably, we found that not entirely a wild idea. You can actually get quite reasonable physics on an end-of-the-world brain. So, yeah, we live on the end of the world.
What are you going to do with this thought? Have you written a paper?
We have, yeah. We've written a paper. You can see, I can show you Ben's poster. It's just on the outside of my door. Do you want me to show you?
Go on.
Go on. So you can see he's telling the story of the ends of the world brain. And
there's an actual hole where you can see.
Yeah, he's done a pretty funky hole, hasn't he? It's pretty cool.
I've never seen that in a poster before.
Yeah, I know, it's good,
Wow.
So you can see here how he's comparing it to the to infinitely negatively curved space. And we were able to make sense of the physics of what was going on by making that correlation. The whole idea of this was we very naturally were able to get, and it showed that if one of these things appears, one of these end of the world brains appears, that it would naturally be like an accelerating universe, by the way. So it was a nice way to get accelerating universe from, well, not quite string theory, but something very string theory motivated. So yeah, nice little hole. That's the nothing on the edge. We live on the end of the universe, literally.
Right there.
So we just live there, yeah, and then there's nothing.
Do you like that you put all this work into a poster and all I care about is that it's got a hole in it?
I didn't put the work in, Ben did.
This episode was brought to you by Jane Street and the sort of people who like our videos, pondering mysteries, solving deep problems. They're just the sort of people who might like working at Jane Street, a world-leading quantitative trading firm. They have offices all around the world, and at the time this video is being released, Jane Street's currently accepting applications for their next round of internships. It doesn't matter what you're into, machine learning, software engineering, trading, this is going to be a chance to work with the best people and do fascinating things. It doesn't matter where you're from, Jane Street will cover all the travel and accommodation for their interns. Last year's intake were from 24 different countries. This is a rare opportunity. You're going to work with amazing people in amazing spaces doing amazing things. Jane Street take good care of their people. Check out the links below for details.
But if you get it right, you can get something like this to form, and it would actually be roughly stable in the sense that you spin it up a little bit more, it's not going to destroy it. Spin it down a little bit, it's not going to destroy it. Where it is vulnerable is to things like tidal forces. So this is much more stretched out than an ordinary planet. If you think it's orbiting some star, then the difference between sort of the force here and the force here